step will take the edge away of that constant classify everything is dog and reweigh things so dogs, the total weight on dogs and the total weight on non-dogs is 50%. So this is sort of the first thing that's going to happen. It's going to renormalize your data, reweigh your data, so that after that, that weak learner, constant, everything is dog, doesn't have an edge anymore. Its edge is 0. So this is sort of the reweighing will take care of that detail. Do you understand? It will pull the information out of that constant hypothesis, everything is dog, reweigh things that afterwards, that constant hypothesis dog doesn't give you an edge anymore. It pulls that edge down. Okay, so that was the first question. Now, I called these learners weak learners. They don't have to be weak learners. If you, of course, put your SVM, fancy thing, fancy machinery, fancy SVM as one of your base learners, it's going to be highly accurate already. It doesn't really matter. The boosting algorithm will take advantage of it and then hopefully get something better than what your base learner, the best base learner. So I sometimes call them weak learners, but it's in some sense comes from the original motivation. It doesn't have to be weak. It can be a strong learner already, but then the combined hypothesis is even stronger. Okay? Good. Now I'm going to give you a big picture where these updates come from. And I do a lot of work in this area. So motivation of these updates. So I'm going to distinguish additive and multiplicative updates. These are extremely loose terms. Technically, what it means is there is a certain regularization used here versus another regularization used here. Okay, but informally, we use additive, multiplicative. I'm going to switch and use linear regression as an example problem, just for fun. And in general, what I want to do is I want to motivate all the machine learning algorithms as a trade-off between a regularization and a loss or an objective that you want to minimize. Right? And this is the trade-off parameter. It often becomes a learning rate. Sometimes instead of having eta here, you put a 1 eta over here, 1 over eta over there. Sometimes you have additional linear constraints, and sometimes no regularization. You just minimize the loss itself. Okay, so, but it's always typically a trade-off between these two things. And now I want to talk about what kind of regularization leads to what. You understand? Very high level. Okay? So this is very important. So here's your setup. It's an online learning setup. You have trials again, and you get a point in Rn, right? An n-dimensional Euclidean space. Your parameter vector is a weight vector. So you predict with your current weight vector dot product. See? Predict with your dot product. You get a label, and then you see how far you were off. So you have a plane, right? You have a plane as your current hypothesis. And then you get a point, and then you're somehow punished by how far you were. Square loss. And then you update your plane. So that's the online setting and I'm going to derive some very basic updates. This is how people started discovering machine learning. Okay? So the simplest update is an additive update. Okay? What's the additive update? Your new weight vector is the old weight vector minus eta times, and this is the gradient of the loss. Okay? So you see, look here, I had as my loss, this as my loss. Do you see that? This is w dot x. This was my loss. Square loss. If I take derivative with respect to w, a derivative, then I get this. Do you see what I'm saying? I'll show you in a moment how to derive it. That's the derivative of that square loss. OK, and I'm going to motivate this update. And I'm claiming there's a regularizer that is implicit here, which is the squared Euclidean distance. These weights, very important, these weights can get negative, right? Because the gradient can go any which way, particularly if you have noise. So it's very important. Now I'm going to do a multiplicative update. The multiplicative update takes the same thing, but it puts those gradients. Now I have to write it component-wise. Here I could write it as vector notation. Vector of all weights is old vector of all weights minus gradient of all weights, derivatives on all weights. Yeah? Good. Now, I can now multiplicative, I have to write it component-wise. Ith component of new weight is ith component of old weight times e to the gradient of the ith component over normalization. See, this is, you see, this is related to boosting. Do you see that? There's these factors, these exponential factors. See the connection? Exponential factors. That's related to boosting. Boosting is in that family. Perceptron is in that family. You see? So you have to see families now. Okay? So this is going to be a relative entropy regularization. Totally different ball game. The parameter here stays on the probability simplex. You see that? Because this is a probability vector, and then this is a probability vector. This is not a probability vector. This is sort of a vector in Rn. They're totally different objects. Yes?
Can you give a bit intuition about why you would choose multiplicative updates? Because the additive one is quite natural in terms of ranking, in terms of gradient. You take a step in the space.
They have different properties. Long story. This one works well when the instances are orthogonal. This one doesn't do anything because your hypothesis is always a linear combination of the past examples. And when you get a new instance, you always predict 0. Whereas this one, in some sense, in these cases, can still learn. It's a long story. There's a paper called Leaving the Span that I did with Vichy. You can look at that. That talks about that. It's a very interesting topic. The updates produced from these different regimes have totally different properties, and we, in some sense, figured out in what case is what family good. It depends on dual norms of the parameters that you have to measure and so forth. Goes beyond the scope. But I want to just sort of make the connection to boosting. Boosting is in this family, I claim. Okay? But this is a very good question, very reasonable question. So here's my trade-off. Yeah? I want to, with my new weight vector, stay close to the old weight vector. Do you see? So that's why I have a divergence. Here I took the Euclidean distance squared. But I also want to get the loss small, right? Because I could see that example again. The loss should be small. So I look at the trade-off between the two. Stay close to the old, loss small. Do you understand the tension? If you have onlineness, uncertainty, you want to stay close to what you have learned before. You want to have an inertia. That's this term. But you also want to get the loss on the last example small. That trade-off motivates, that tension motivates your online algorithm. I claim if you use Euclidean distance squared, you're going to get additive updates. This is the learning rate. You got the picture? Trade-off, right now Euclidean distance squared. OK. So what I do is, how do I solve this kind of a thing? Well, I take derivatives. Machine learning, you mostly need to know how to take derivatives. Integration, we don't need that much. But derivatives, you need to learn how to do. OK, so I took a derivative of this thing. So the Euclidean distance squared is a quadratic thing. So that provides you with this term. And then here's again the gradient of the loss. The 2's comes from the quadratic, but they're going to cancel out. Now, if you take this little thing, set it to 0, and solve, what you're going to get is the following curious update. You're going to get new weight is old weight minus eta times the gradient. Cool, right? Minus eta times the gradient. Now what you're going to get, actually, if you do look at this very carefully, you get the new weight is the old weight minus eta times the future gradient, the gradient at wt plus 1. So we call this the implicit update. And this is sort of the pretty update. Now, we usually don't use this implicit thing. In this case, you can solve it, and it is in this linear regression case. But in general, you can't. So we just approximate the t plus 1 here by the old gradient. But there's a huge difference between these two in some cases. This is really, the implicit update is much more principled. And Vichy wrote papers on the difference. He will talk about it. If you go from here to here, you lose basically everything. This is really the motivation to be trusted is the trade-off, the implicit update, and that's a kludge in computer science language. A kludge. Okay? Quick and dirty, works in practice, maybe. Okay, so that's the implicit update. Now, so you understand, derivatives gets you the additive update. So this is the additive update. Another way of seeing these kind of updates is it's skiing. You ski down the steepest slope. Okay? So this is going to be geometric, it's going to be all intuitive, and so forth. Now, how do we get the multiplicative update? Totally different scenario. Multiplicative update, same setup. My regularization now is a relative entropy. And I'm going to harp about relative entropies in a moment. What they are, where do they come from? Because they're a little bit more mysterious. Okay, here's your relative entropy as your regularizer. Again, same trade-off to the square loss. You got the idea? Trade-off with the square loss. You want to stay close to the old weight vector, now measured in terms of relative entropy. But you want to get the loss small. Now your parameter is a probability vector. Fundamentally different. And you want to minimize this. Now, OK, look, you want to minimize this, but you have a constraint. The constraint is that your weight sum to 1. So you need to do a Lagrangian. Relative entropy plus loss, Lagrangian. Right? Lagrangian for the constraint that things sum to 1. That's a technique that you have to learn. Very important. And now I want to minimize the Lagrangian and enforce the derivatives with respect to the parameter vector w to be 0, as well as the derivative with respect to the Lagrangian to be 0. OK, so you take a derivative with respect to wi. Then the relative entropy derivative, it was wi log of the ratio. You take the product rule, and you get two terms, a log wi over wti plus 1. And here's the familiar gradient of the loss. And then from the Lagrangian, you get the lambda. So here's the Lagrangian again. This gives you log of the ratio plus 1. This gives you the normal gradient of the loss. And this gives you a lambda. OK, so now you're going to set this to be 0. So you were wondering, how come do those same gradients appear in the exponent? Well, if you take derivatives of the relative entropy, you get a log of the ratio. Yeah, clear? Log of the ratio. When you now solve for your weight, wt plus 1I, you're going to push that stuff here into the exponent. Right? If you solve, you have to exponentiate. Gradient appear in the exponent. Lagrangian is still here constant. But the Lagrangian, if you take a forced derivative with respect to the Lagrangian to be 0, that means that this factor has to do the job of normalizing all these weights so that the total weight on the wt plus 1 is 1. Yeah? So this is a little bit too much in a talk. I apologize. But you get then this update. Again, the implicit version. New weight, old weight, times e to the minus gradient at the future. At the future. And then here's the explicit one. Questions? So you see that different regimes use the same gradient but end up with a different update. What time is it? I have bad eyes.
9:40. So you
Okay.
have another 45 minutes.
Okay, good, good. So again, implicit update, explicit update. You got it? So relative entropy, so additive versus multiplicative update. You see, this is a factor now. If before, you know, if you want to educate your child, you can whack it this way or that way, right? You do it additively, then the guys that were, you add something to correct, and here you multiply by factors that are either bigger than 1 or less than 1. Right? Actually, it's a very deep question. What learning algorithms happen in nature? Okay, I have my own theories. I have philosophies about everything. I think it's multiplicative, but to prove that, we don't know. I have people that play around with simulating cat brains with supercomputers, and they claim these multiplicative updates happen in the brain. Who knows? So I can explain these additive versus multiplicative updates in a different way, using differential equations, if you have a physicist background. What's gradient descent, the additive update? Oh, I claim it's simply Wt dot equals minus the gradient. Dot is a derivative with respect to time. It's this thing. It's the physics notation. Yeah? So basically, what this means is you ski down the steepest gradient, all the way down. That's what you do. That's what this equation means, this differential equation. Now, if you discretize this differential equation, then you get Wt plus h. You do discretize this. You write this derivative as this ratio. You set eta h equals 1, and you get this update. Now, people in differential equation, the implicit versus the explicit update is here again. People in differential equations know that what you should do here actually, you should approximate the gradient at t plus h. So this should be t plus h. This would be t plus h. And if you did this, you would get the implicit update. And that's better. It's more stable. This is called Euler discretization. And if you approximate at the future gradient, it's called forward Euler. Don't know whether you've heard about this. Okay, and then there's something like intermediate Euler and so forth. People know about this. So again, even in differential equations, the implicitness makes more sense. How do you get the exponentiated gradient algorithm? Not gradient descent, exponentiated gradient algorithm, multiplicative update. You now take log of Wt dot. So this is now a vector, and then the partial derivatives with respect to time is minus eta the gradient. Again, I can discretize it. I have to now write it component-wise. So I have this difference of logs divided by h. Here again, use the old gradient for simplicity. Then I have this. And if I set eta equals 1, I have this. And I don't have the normalization here because the normalization would be an outside constraint, and it's more complicated. But it's the same flavor. It's essentially the derivative of the log. Okay? So additive versus multiplicative updates. You got it? Okay. Good. Now, I explained this in the context of online learning, but there's no big difference. You can also have batch learning. In the batch learning, you do trade-off between regularization and total loss on the whole batch of examples, not just the last one. But the same issues appear. You have additive versus multiplicative updates. OK. And essentially, the regularization determines how the parameter space is being searched. Again, there's two main regularizations: squared Euclidean distance, relative entropy. OK? Now I'm going to give you the big picture. Classify all the machine learning algorithms you know in terms of those two. It's really funny. There's very few machine learning algorithms. In these lectures, they tell you all these fancy things. There's not that many. I claim there's only two basic schemes. Of course, I'm being facetious. OK. See, I'm a professor. I can say anything. So you have two families of updates. Euclidean distance squared. As a professor, you're a professional big mouth. The problem is, if you have kids, they turn out to be big mouths, too. And then you have a problem. OK, so, because they learn from you. So you have squared Euclidean distance. What belongs to that family? To that family belongs the Woodrow-Huff update. That linear update that I showed you is the Woodrow-Huff update. It's the first machine learning algorithm, along with the perceptron, that was ever discussed. It's called the LMS rule, right? Sorry, I didn't mention the name. This kind of update, it's called the LMS rule. Lean mean squared error something, or the Woodrow-Huff update. So the perceptron is another case. Perceptron is the case when you take, instead of taking square loss, you take a hinge loss. OK? Then you get the perceptron algorithm. That was first machine learning algorithm, right? I showed you already some exponentiated gradient update that corresponded to this. The corresponding update here is called the Winnow algorithm. The Winnow algorithm was the first multiplicative update invented by Nick Littlestone in his thesis in 1989, which started this whole thing of online learning. He was really a pioneer in many things. He now lives in the Santa Cruz Mountains. Really fun guy. So backprop is another example of a gradient descent algorithm that the neural network people did. Okay? Additive update to the weights. Support vector machines is a batch processing algorithm, but you see that it's an additive update in the following sense. So another way to distinguish these different updates is the following. You see here that your weight vector that you have, this is a linear combination of the past examples, and you add another factor times the new example. What happens is, at any given point in the additive updates, the weights are linear combination of the past examples. The multiplicative ones, logs of the weights are linear combination of the examples. If you take the logs of the weights, they're linear combination of the examples. Fundamentally different. You can see that support vector machines, the weights are linear combination of the examples. So it belongs to that family. Now, there's Winnow algorithm, there's the weighted majority algorithm, expert framework, online learning. I don't know whether you have this covered in this tutorials. The Bayesian update that everybody does belongs to the multiplicative family. You can motivate it using a relative entropy trade-off. Totally cool. Okay? And boosting belongs over here as well. Okay? The boosting objective is just very messy. I will talk about that in a moment. I'm just doing slow build-up. Yes?
What exactly do you mean with Bayesian update?
The Bayes rule. Yeah? You can motivate Bayes rule in terms of a trade-off. So Bayes rule, you can motivate here. You do some kind of relative entropy. Actually, it's a relative entropy to the prior. Relative entropy to the prior, eta times loss, and the loss is an expected log likelihood. And if you do that, bam, Bayes rule comes out. Different talk. Okay, so here's the families again. Right? Additive family, multiplicative family. Now, they have totally different properties, I claim. Essentially, what happens is, if you have additive updates, they ignore small weights. Why? You square things. Right? If you take something small, 0.001, you square it, it's gone. So you ignore small weights. So what happens is you end up with an update that ignores small things. And that has major implications. This one, so in other words, you can always use small weights to interpret your data. And if you have a lot of weights, then the lot of small weights can be used to always randomize, to fit random parts of the data. And sometimes this doesn't work. Because you're not regularizing on the small weights. You're not punished for using small weights. Intuitively, the relative entropy is a smoothed one norm. It doesn't ignore small weights, but they add up. This is rough. Okay. Another way to see it is the squared Euclidean is the log of a Gaussian. Why do we use Gaussians? Well, why do statisticians use Gaussians? Well, we're interested in log likelihoods, and we know how to do quadratics. Why do we know how to do quadratics? Because the derivatives are linear. Okay, so we do all these things because we can. Gaussians are easy, we can. This is easy, we can. Support vector machines are easy. Why? Because it's a quadratic problem. Derivatives of quadratic is linear. We want to do much more complicated things, but we don't know how. And we have no idea what nature does. Biggest frontier in machine learning is to figure out what's happening in the brain. We don't know. I was just at Valiant's Turing lecture. He used all kinds of complexity theory to define what is an evolutionary algorithm. It's basically has a bunch of creatures. A Turing machine modifies the creature, and then another Turing machine selects good things from it, and it has to evolve to something. Well, he has no concrete examples where this whole scheme of complexity theoretic thing with polynomial time steps along the way does anything interesting. And yet nature does it. So we don't know. We have no idea. Okay, of course, I have my own theories, but we'll do that at the end for fun. I'll do a fun lecture at the end that what I think is happening. Okay. Now, so what I want to talk about now is where does the relative entropy regularization comes from? I want to talk a little bit more about that. What is that animal? And what I know about it. Okay? So this is coding theory. You want to send a symbol on a channel. Yeah? Good. So here's your symbol. You have 4 symbols. 4-sided die. Okay, so it's a tetrahedron. And here's the probabilities. A half, a quarter, an eighth, an eighth. Now, this is what you use as your measure of surprise, minus log of pi. So you are a little bit, you're a little bit surprised when you see the half outcome, but if you see the eighth outcome, you're more surprised. Right? The surprise is measured in bits. You understand? Okay, good. Look here. If you're absolutely certain in your outcome, then there's no surprise. On the other hand, if your probability is 0, then minus log of 0 is infinity. You're totally surprised when you see that outcome. So that's the measure of surprise. Cool? If it's 1 over 2 to the I, you have I bits of surprise. Right? So that's your notion of surprise. Now I'm going to get you to entropy from that. Okay? Entropy. Okay, so the entropy is the expected surprise. pi log 1 over pi. I wrote it now as 1 over. You can also put the minus outside, right? There's two ways of writing it. So this is your expected surprise. So in this particular example, it was 1/2 times 1 bit, 1/4 times 2 bits, 1/8 times 3 bit, another 1/8 times 3 bits. Okay? You understand? So this is, in this particular example, your surprise was 1 3/4 bits. Okay, now let's talk a little bit about what is this entropy function. It's going to be very important because it's a very important regularizer. Okay, look here. In 2 dimension, you have 2 events, p and 1 minus p, because they have to sum to 1. If you plot the entropy, you get this thing. Okay, if p is 0, then your expected surprise is 0. The most uncertainty you have when p is 50-50. That's the most uncertain distribution. So that's a maximum here, and then your expected surprise is 1 bit. So now what I'm now going to do is I'm going to plot these things on the simplex. Okay, what is this object? Okay, so I'm in 3 dimensions. I have 3 things. Here I have 2 things, p and 1 minus p. Now I have 3 things, p, q, 1 minus p, 1 minus q. So in other words, I have 3 probabilities, right? And then there's this little, and since I constrain things to 1, there's this little triangle here. I constrain things to 1, and I have non-negative, so there's this triangle, and now I take that triangle and look at the top. Do you see that picture? I look at the top, and this means all the probabilities on the first event. This is sort of 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1. And then these are all possible distributions on 3 things. Because I'm constrained to sum to 1, I have a 2-dimensional object. I look at it from the top. Cool? Implicit plot, you can do it with Maple. OK. So the entropy is the largest right here. That corresponds to the uniform distribution. A third, a third, a third gets you here. OK. And what happens is, in general, if you have a uniform distribution, your entropy is going to be, the probabilities are 1 over n, and then you sum up log of 1 over n, which is log n, and you sum it up, and it sums to 1, so the entropy is log n. So the highest entropy is when it's the uniform distribution. You don't know anything. Your expected surprise is the largest. At the corners of the simplex, your entropy is 0. So it's something that sits on top of the simplex where the corners are 0. Here's a 2-dimensional simplex, which is just a line, and it's 0 at the end. Got the idea? OK, good. Now, good. So you assign symbols. What's a code? You assign symbols to bit strings. This is Shannon type stuff. Big pioneer. Any sequence of code words must be uniquely decodable. Right? That's the condition you have. And now you can look for a particular code for an assignment of the xi to bit strings. You can look at the expected code length. Cool? Expected code length, pi times the length of the code word for xi. Now, the optimal code, for the optimal code, the expected code length is minimized. Good. You can show that the entropy, upper and lower bounds, the best code, expected code length. by +1. And the Huffman codes are optimal. If you want to read more, you look at the first 5 chapters of Cover and Thomas. Very nifty book to read. OK. So I will harp a little bit on this, and then I'll show you more plots. I'm going to have to switch. Can you see this? OK. So here I did some Huffman code. What? So what I did here is, here's your little symbols. They were, I think, 1/2, 1/4, 1/8, 1/8. How do I build a code? This is Huffman code. David Huffman, he was from Santa Cruz. I got my beekeeping equipment from him. He died of cancer, unfortunately. So what happens is, how do you build a Huffman code? You look at the smallest 2 symbols, and you combine them. You build a little tree. You combine them. And now you label this as 1/4 because 1/8 plus 1/8 is 1/4. OK, now you have 1/4, 1/2, and 1/2. Now you combine these 2, and you get 1/2. And you combine it again, you get this symbol. And now you have a little tree, and that gives you a prefix code. Because let's say going up means 1 and going down means 0. So this is 1, and this is 0, 1, and this is 0, 0, 1, and this is 0, 0, 0. So this is a prefix code. And you can pick, so the general scheme is you pick the smallest 2 and you combine them. Build a tree that way. OK. And we already computed at some point what the expected code length was. I think it was 1 3/4 of this. Now, you can also, let's say, put the uniform distribution on this. Right? That's 3 events now, 3-sided coin. You combine the smallest 2, and then you combine again, and this is your code. What's the entropy? What's the expected code length of this? The expected code length is this, which is 5/3, 1.66. But log base 2 of 3, the entropy is a little smaller. You see? So the entropy is always close to the expected code length that you produced by the Huffman code. The scheme is like this. Huffman code is +1, optimal code. In the uniform distribution, this is log n. And this is log n plus a little bit. In this example, log n was this big. The best code you built for the uniform distribution was 1.66, a little bit bigger. Okay? So this is a very cute little thing. It's expected code length related to the entropy. OK, now, next source, laptop computer, center screen. Oh, I did the same screen. This is, they flipped the screen on me. It's cross. OK, fine. Good. Why is this one? Oh, come back. OK. OK, so the entropy measures relationship to expected code length. OK, so now here's what we're not interested in entropy. We're interested in relative entropy because we want to measure the distance between two distributions. But technically, it's not a distance. We call it a divergence because the triangle inequality doesn't hold. So this is your divergence. We usually use delta to denote the divergence. You can write this as This term minus this term. This is the expected code length of the best code book for Q. The best code book for Q encodes the event I as log 1 over Qi. But you take the expectation with respect to B, and this is the expected code length of best code book for P, and the difference. This is the expected code length of the best code. This is the expected code length if you use the wrong code book. Use Q's code books, but you measure the expectation with respect to B. Since this is the best, it's going to be bigger than 0. So it's the expected additional code length. That's what the relative entropy is. Expected additional code length that you get by using the wrong code. How does relative entropy relate to entropy? Well, if you measure relative entropy to the uniform distribution, remember I had this plot where everything was in the center? So that was the uniform distribution. I measure relative entropy to the uniform distribution. Then I get this, minus p log I. This one becomes log n, so I get log n minus the entropy, which is always bigger than 0. And it's 0 at the center of the simplex. In general, the relative entropy is non-negative, but it's 0 if and only p equals q. Okay, is that clear? So if you look at it, I'm going to bring more pictures up in a moment. Okay, here was the entropy. It's a concave function. It's related to the relative entropy to the uniform distribution. Now, since you have a minus here, this is a convex function. So the relative entropy to the uniform distribution is this thing flipped upside down, and then this thing flipped. The picture would look the same, but if you measure entropy, this is high. Relative entropy to the uniform, this is low. This is actually 0. OK. Now, so this is relative entropy. So I'm teaching the beginnings of information theory. Now, if you looked at this relative entropy, well, there's two variables, right? Two variables. Which should be your new parameter? Should it be the first one or the second one? What do you think? First or second? Is it symmetric, entropy? No. Entropy is not symmetric, and first and second parameter are fundamentally different. I've used both in machine learning, but mostly we use first parameter. So let me show you in plots what's happening. In plots, this is first argument. Okay, first argument. It reaches into the corners, as you see here. The target distribution was a little bit off center to make a point. And it has nice sort of plots. If you cut across here, I'll show you some cross cuts in a moment. And this one is fundamentally different. If you take the second argument as the variable, it's extremely steep at the boundary. Let me cut across this and do a two-dimensional plot. I think I have one up. Didn't have time to load this. This is the one where the first one is the argument. It's nicely quadratic. As a matter of fact, in general, this would look like this. It's sort of linear out here and has a little quadratic piece and linear here. That's the first argument plot. The second argument plot is a tub. It looks like this, as you see here. See, it goes towards infinity at the boundary. Yeah. OK, and Euclidean distance squared is down here. It's perfectly parabolic, as you will see in a moment. view, slideshow. Give me slideshow. Okay, this is Euclidean distance squared. For Euclidean distance squared, it doesn't know about the simplex. It just puts perfect circles. Sometimes it's a wobble circle, like a bowler hat, right? A high-dimensional Gaussian, if you have variances. But it's always, it ignores the simplex. It ignores the non-negativity constraints. It's not suitable for regularizing on the simplex. If you want distributions, there's one divergence, relative entropy, typically with a first argument. Don't use Euclidean distance squared on the simplex. Why? What you would have to do is you do an update, you step outside, and then you have to project back. And that usually involves forgetting. Everybody does these updates because they're easy to analyze and to compute, but they're not the right thing. Relative entropy, if you work with probability distribution, relative entropy is the right notion of progress, the right divergence. Very important to understand. The Bayesians got it, but they don't know that they got it because they don't know how to motivate it usually. They just get the update from that pastor that did it, the English pastor, Bayes. You know, this guy did nothing. He just wrote down one formula and he became famous. You could have done that. But it's all about timing, you know. Okay, so this one here has infinite, it goes to the boundaries at infinite. I have used this one too. It's a very long story. We developed an update based on this. It's sort of, because this goes infinite, it helps you to not forget. You always have to stay close to a boundary, to your last parameter vector, and you cannot forget the last parameter vector. Totally different. But boosting over here. Exponentiated gradient algorithm over here. Bayes over here. Most of, okay, 99% of machine learning is gradient descent, additive updates. Why? Because it's easy and we know how to do it. If you look at statistics, a lot of it is Gaussian modeling. Gaussian everything. Okay? That's gradient descent. A little bit of it, via Bayes in particular, Bayesian analysis, you are in relative entropy world. Okay? So that's your machine learning for you. Yes?
I'm a bit confused when you say like there's these two big distinctions.
Yes.
Between, all these methods fall
yes.
into first type of regularization. Because the notion of regularization, from what I understand, at least in the regression cases, we use regularization so that the weights don't get weird.
Yes.
And,
yes.
We don't necessarily need any regularization in the form of a probability simplex, right? Say if you're doing regularization for linear regression, all you want is sparsity, for example, right? Like if you do.
Right. Okay. So you mentioned many things right now. Okay. Okay. So slow you down. One moment. I answer a few things. Machine learning all talks about the same things all the time. Okay. First of all, in an upshot, additive versus multiplicative update. Additive, you got that? Multiplicative, factors. Okay? Sparsity. Additive updates are very bad at sparsity. Why? Small things don't hurt. Small things are going to linger around because you're not punishing for them. They're going to sit around forever. As a matter of fact, you could say these updates, the art of this update is interpret your data using small weights. Why? Because small weights are not regularized. They're squared away. They're not punished in the regularizer. Okay, so if you use this together with sparsity, totally crazy. Doesn't work. Has nothing to do with sparsity, no matter how good the cell is. Okay, if you want to do sparsity, one way towards sparsity is use one norm regularization. That helps a little bit because then small weights count because they add up. Relative entropy is a smoothed one norm. Ideally, you want zero norm, which is kind of a term for counting the number of non-zero guys. Nobody knows how to do that. That's NP-complete. Okay? Questions? Did I answer some?
What's the notion in terms of entropy
Entropy regularization. Okay. If you want to go for sparse solutions, during the learning, you need to spread the weight because you have uncertainty. You cannot learn with sparse hypotheses because you only get feedback about the sparse things that you put any weight on. So during the learning, you have to spread. So there's this contradiction. You want to learn something sparse, but you have to spread as you learn. So so entropy does this, and Euclidean distance squared also, because it does it, but it does it the wrong way. But entropy spreads the weights as you go on. And in some cases, let's say in the case of Winnow, you have hints that the multiplicative updates are good when the comparator that you compare against is sparse. Long story. OK. Did that. OK, I'm going backwards. Not a good idea. You always go forward. OK, questions? So the question that we should ask ourselves, what optimization problems motivate boosting? OK? I'm going to claim they're going to use relative entropy as the regularization and a bunch of funny, a very complicated objective, unfortunately. And I will start with that objective a little bit because it's pretty hard to get, and you can look at it, and then when we start the next lecture, you will know a little bit about that objective at least. OK? Yes, I'll get to that in a moment. And, huh? Go. Yes.
On the last slide, on those two plots, when parameterizing the entropy, is the solution search much easier when using either of the two?
Yes, this is nicer. This is a mess. Right, because here it becomes this e to the gradient, the multiplicative factors. And here it's complicated things that go to infinity as you go to the boundary. Okay? So this is what we're going to use. This is what we're going to use in our regular, when we use relative entropy. Okay, both work as a barrier. Both get you towards the center of the simplex. The slope around here at the boundary is positive. It sends you to the inside. It sends you to the inside. This sends you to the inside in a very steep way. It's infinite at the boundary. But this still sends you to the inside. So both work as a barrier. Okay? OK. OK, now what is the loss objective of boosting? And what happens if no regularization is used? OK, that's how we're going to start now. No regularization typically doesn't work too well at least when you have worst case data. Okay, no regularization works well if you have a lot of randomness in your data. If you have a lot of randomness, then the randomness of your data in some sense is a smoothing factor. And you can sometimes get away with no regularization. But if you somehow have worst case data, then you need to put an artificial regularization. The regularization, you can view it as having additional initial examples. You can view it as a prior in Bayes. There's many motivations. Everybody comes up with the same thing. In machine learning, we bypassed all the stuff that the Bayesians did. We use these kind of divergences. We use delta as our notation. And they are Bregman divergences. How many people have heard of Bregman divergences? Some, yeah. So relative entropy and Euclidean distance squared are the paradigmic two main Bregman divergences. I've done a lot of work on generalizing machine learning to gazillions of Bregman divergences. And it turns out that Bregman divergences are a sweet spot because the parameter divergence, you remember I explained everything in terms of trade-offs. Here was a trade-off equation. Like that kind of a thing, a trade-off, relative entropy loss. Well, it turns out that this is a Bregman divergence and this is another Bregman divergence. So the setup is often trade-offs between two Bregman divergences, one in the parameter domain and one in the loss domain. Separate story. If you look at previous summer schools, I did tutorials on Bregman divergences in online learning.
Can it hurt you if your data has a lot of randomness
It is not as crucial if you have a lot of randomness.
Can it hurt you, though, if you use a regularizer when you
You still, you introduce a bias or how you go through the solution space. Yeah, sometimes you don't want to listen to the noise, right? You don't trust the noise, so you trust the regularization more. Blah. You understand? But which regularization you pick when you have noise is very important. Why? If you use gradient descent and you have noise, then you listen to all the small errors introduced by the randomization. Very dangerous. Gradient descent with noisy data is sometimes very dangerous, whereas the information theoretic one is better at ignoring irrelevant parameters. If you want to look at that, look at the paper Leaving the Span. OK, good. So now I'm going to talk about boosting. I'm going to pick this up on Monday as margin maximization. I'm talking about what is that complicated objective that you want to minimize in boosting. OK? It's a complicated object. In linear regression, it was a trivial thing. Square loss, you all know about this. In boosting, it's a messy thing. OK, good. So here is, now I have to go back to the boosting slides, and I explain to you what the work up to the objective. Do you remember this was the accuracy of the teeth hypothesis on the nth example? It was +1 if the teeth hypothesis interpreted the nth example correctly, and -1 if it's incorrectly. And this is the weight. So this is the weighted edge. Okay, it's the edge. Okay, so it's the edge of H2 for distribution on the examples. It's the weighted accuracy. That's one object. That lives in the D domain. There's two domains, the D domain and the W domain. D, distribution on examples, W, distribution on hypotheses. Sorry, it gets complicated because you have two sets of weights and there's duality. It confused the hell out of a lot of machine learners for a long time, but now we're sort of getting smarter. We did some work and clarified it. But it's messy. I can't change it. The second set of weights is the weights on the hypotheses. Here's your hypotheses. Do you remember these were the hypotheses times the labels? Do you remember this? The hypothesis times the labels. That's how I got this. This is the teeth hypothesis times the labels. You combine those, and a weighted combination of those, that's going to be the margin of an example. I'm going to show you a picture in a moment. So let me, since everything relies on these U's, I need to explain to you what those U's were again. So I have to go back. Apologize. So I'm now back to here. OK, here is the slide that explains the U's again. Again, your labels, your hypotheses, and these are the U's, the product of the two. OK? Perfect means the label, these two agreed. Opposite, they disagreed. Neutral. Yeah? So this is an accuracy of the nth example. The edge is the weighted accuracy, weighted by the distribution. You got it? So now let's go back. And I'm going to, I've worked on, I enjoy visualization. So I've worked on visualizing this in various ways. So look here. Here, weighted. This is something where I sum over the examples. So I'm evaluating the hypotheses. This is the edge of the hypothesis T. Here, I sum over the hypotheses, the T, the number of iterations. And I'm evaluating an example. Edge of a hypothesis, weighted accuracy of the hypothesis, margin of the example. Fundamentally different. OK. So in boosting, what happens is the edges of the past hypotheses are pushed down. Do you remember that dog example? If 90% of your pictures are dogs, your first weak learner is going to be constant dog. After that, its edge is going to go down to 0. So what happens is the edges of the past hypotheses are pushed down by reweighing your examples. And you minimize the maximum edge. So that's the loss. Minimize the maximum edge. So it's a min-max. It's complicated. In the dual domain, you will see the moment, you choose a convex combination of weak hypotheses that maximize the minimum margin. Pictorially, you have points, and you have a plane. This is the margin of a particular hypothesis, positive margin. Yeah, this is the margin. If you multiply the label, these are negative, so the margin is going to be this. The maximum minimum margin is the closest one, so that would be this one, you see? Now, this is the wrong picture, because it's a geometric picture. I cannot plot for you the information theoretic picture. I'm plotting you the geometric picture, alluding to the fact that margin has something to do with the distance to the hyperplane, but it doesn't. In SVMs, it does. But this is sort of a one-norm margin, because all the things are with respect to the probability simplex, and the weights are normalized to 1. So I cannot even draw for you the one-norm margin. Yeah? But it is defined this way. Yes? Huh? No, you meant this slide? Yes.
Does that kind of explain how SVM and boosting are similar in this case? So rather than physical distance, because it's Bregman divergence, then this is...
It's not Bregman divergence. It's you have a dot product, and you either divide by, you take the dot product, and you divide by the 2 norm of the weight vector, then you have the Euclidean distance, or the 1 norm of the weight vector. That's the difference. 2 norm versus 1 norm. The 2 norm is what I'm plotting here. The 1 norm is what was used in boosting. Is that clear? So it's a screwy, it's not the normal margin. The SVM margin is fundamentally different. It's geometric. This is the 1 norm margin. OK, so what's the connection between the minimum maximum edge and the maximum minimum margin? Huh. Welcome to the mess. It's the same. And that was done by von Neumann in 1910 or something like that, one of the heroes of computer science. So technically what happens is minimum distribution over the examples, maximum over your hypotheses. You look at the edge, weighted edge, you understand? And then here, minimum distribution over the hypotheses, weights, maximum over the examples. This is the 1 norm margin. It's a 1 norm margin because you are constrained to work on the simplex where the weights sum to 1. Yeah? These two are the same. It's linear programming duality. This is the modern way of doing it. Von Neumann didn't do it that way. He did it game theoretically. Huh? Yes, I'm running out of time. So I'm now going to give you an overview. Even if you need to decide whether you want to go to the beach. No, you don't have a beach here. So if you want to do something else, like play in the cornfields, no, we used to play in the cornfields a lot. So what I'm going to do, I'm going to explain this minimax in terms of game theory, rock, paper, scissors type of games. That's how von Neumann did it. Minimax equals max min. There's a relationship. Okay? So then I'm going to talk a bit about boosting brings this margin up. Here's the margin. You add your weak learners, and your margin goes up until the optimum margin. And the goal is to do this as quickly as possible. I explain boosting that way. I'll work this out. And here is the minimax theorem. Then I'm going to generalize it to the noisy case. And this is the objective of boosting in the noisy case. And you can ignore any regularization, and just do this, minimize this objective, then you get LP-boost. It's a linear programming problem, believe it or not. But if you're smart, you add a little bit of relative entropy. Here it comes. So you take this minimax, but you add relative entropy to your objective, and that smoothens things out. And then you get what we call entropy regularized LP-boost. LP-boost is without the regularization. If you add the relative entropy, entropy regularized LP-boost. And that makes all the difference in the world. I show you simulations that show the difference. If you don't have the regularization, we'll run this thing. It's very brittle. If you do the regularization, it becomes very smooth. So let me show you. Oh, you have to go out. See here, you can kind of see it becomes very brittle. It jumps always to the boundary. It's a useless algorithm, classically bad algorithm. It's too sparse as it goes along. And if you do this other algorithm, the entropy regularized LP-boost, it's more smooth. This was done, Karen Clother helped us with this, and it's more smooth. And if you tune the learning rate, it becomes even more smooth. So these are these kind of different things. Then I'm going to finish. I talk about AdaBoost again, where it comes from. And then I give an overview of different fancy boosting algorithms and their optimization problems, and show why LP-boost doesn't work, etc., discuss lower bounds. OK? So hopefully we'll have some more fun. Any questions? Last questions? I hope you got a basic introduction into what boosting is, introducing connections, additive versus multiplicative updates. At the end of the lecture, I will talk about, my last lecture will be on connections to biology and evolution. Multiplicative updates are crucial in evolution. Natural selection, classical multiplicative updates, and I will talk about all kinds of connections to biology. It's going to be a totally wild, interesting thing. OK? Thank you.